Good afternoon. My name is Julia Jones, and I am working on research at the Applied Physics Laboratory here at UW-Parkside. Our current research group at Parkside consists of myself, Andrew Faustino, and our advisor, Professor Home Kendall, and we are working on the nanofabrication of an SIS tunneling Josephson junction device. In this presentation, I will describe to you Josephson junction devices, their applications, challenges involving the fabrication, and the successful results of our new design and fabrication methods. An SIS Josephson junction is a nanoelectronic device containing an extremely thin layer of an electrical insulator sandwiched between two superconductor layers. So S stands for superconductor and the I stands for insulator. What's groundbreaking about these devices is that electric current can flow through the junction even in the absence of an electric voltage or current source. Josephson junctions are prevalent in many areas of modern technology. They are used in squid biomagnetometer sensors, qubits, rapid single-flux quantum circuits, and terahertz frequency detectors for a wide range of applications, including magnetocardiography and brain imaging used in medical facilities, quantum computing, geophysical measurements, and NASA and military applications. Superconductors are materials that conduct electricity with no resistance. This means that unlike the more familiar conductors such as copper, a superconductor can carry a current indefinitely without losing any energy. However, in order for a material to exhibit superconducting properties, they have to be cooled down to a very low temperature. The temperature at which superconductivity occurs is called the critical temperature, or TC. We are currently working to fabricate a high-temperature YBCO-based Josephson junction device with TC value above the boiling temperature of liquid nitrogen, which offers many advantages over the conventional low-TC superconductor-based devices already on the market. For example, in hospitals, the current systems I mentioned have to use liquid helium as the coolant. With our high-temperature devices, systems could instead use liquid nitrogen, which significantly decreases purchasing and operating costs and is much more convenient for medical personnel to use. It's estimated that we can cut the total cost in half with our high-temperature junctions. If systems can be utilized more easily and for about half the price, imagine the opportunity for widespread distribution within hospitals, especially those with limited resources. The development of a well-controlled and reproducible YBCO-based Josephson junction is very challenging, since in order to provide high critical current, the thickness of the insulating layer must be only about a nanometer thin, which is 1/1000th of a meter, while maintaining high electrical resistivity. The critical current combined with the normal state resistance of the device make up the ICRN product, or merit figure of the junction, which directly relates to its efficiency. Finding an effective insulating material for our device is one of the first challenges our group faced. Numerous attempts at fabricating different types of junctions using PBCO as the insulator have been made, though without successful results. The junctions made with PBCO were either too low in electrical resistance, possessed minimal value of IC, or had a TC value below the liquid nitrogen boiling temperature, which is 77 Kelvin. Recently, though, we developed an excellent oxide insulator, 110 type gallium doped PBCO, or PBCGO, by 20% copper substitution. This insulator has very similar lattice structures, thermal expansion coefficients, and thin film growth conditions compared to our superconductor YBCO. Plus, its electrical resistivity is about 5 orders of magnitude higher than that of the PBCO thin film at 77 Kelvin. My poster is titled Growth and Structural Properties of Heterostructure of 110 YBCO PBCGO, and as it implies, we are reporting on the nanofabrication of a YBCO PBCGO bilayer, which contains the first two layers of the SIS sandwich structure. We fabricated high-density disks of YBCO and PBCGO using solid-state reactions and a high-temperature electric furnace here at Parkside. Then we deposited an excellent quality 110-oriented YBCO PBCGO heterostructure using pulse laser-based thin film deposition technique at the Oxide Laboratory of UW-Madison. The pulse laser deposition system uses a high-energy laser to ablate the disks, and then deposit the materials atom by atom onto a template called the substrate for each layer of the device. After fabrication of the bilayer or heterostructure was completed, we conducted many tests to measure its lattice structure, surface morphology, and electrical properties. The atomic force microscopy measurement shows about 1 nanometer root mean square roughness in our heterostructure, and additionally it contained no cracks on the surface of the film. The low-temperature electrical resistivity measurement showed the critical temperature value of the heterostructure to be 82 Kelvin, which was close to the TC value of a single layer of YBCO, thus demonstrating no significant proximity effect. The results of our various tests confirm that we have optimized the growth process of the heterostructure, which yields excellent thin film properties, such as the high ICRN product I mentioned earlier. We are currently working on adding the final superconductor layer, which will complete the trilayer structure and nanofabrication of the SIS junction. This completed Josephson junction will undergo even more testing to ensure it is high quality and reproducible. Every day, the scientific community works to learn more about the world we live in and how we can benefit our lives from that knowledge. Our research on the development of high-temperature Josephson junction devices is an example of such work. System simplicity, higher efficiency, and low-cost production are all benefits of this cutting-edge technology we are in the final stages of fabricating. Thank you everyone for attending this student showcase and listening to our research, my research advisor, Home Condell, and Parkside and the YSIS and UW system for the funding to make this research possible.